For the next lesson in this unit, we're going to be taking a look at similar triangles. Similar triangles have the same shape and different sizes. You can think of this kind of like taking a photograph of a person. In real life and in the photograph, they have the same shape, but they have different sizes. When we're looking at triangles, having the same shape means that they have the same angles. And having different sizes means that they have different side lengths. To solve these kinds of problems, what we'll need to do is match up the sides and the angles. Sometimes in order to do this, we might need to spin the triangles around to make sure that the corners line up in the correct way. In math, we love to use symbols instead of words, mostly because we're lazy and we don't want to write out full words. So today we're looking at a new symbol, and it's this tilde or squiggle sign. What this says is that triangle ABC is similar to triangle DEF. So the squiggle tells me that the triangles are similar. And we already said that means that they have the same shape but different sizes. So let's take a look at some of the properties. If I tell you that triangle ABC is similar to triangle DEF, that tells me that all of the matching angles are equal. So another word for matching is corresponding. In this picture here, I can see that angle A matches with angle D. I can see that with the two circles. I can also see that angle B has a little X, and so does angle E. And finally, angle C matches with angle F, and they both have that filled-in circle. The second property that I have is that if I were to compare matching side lengths, I would find that I'm always multiplying by the same number to get from one triangle to the other. So perhaps I'm doubling in size, or I'm cutting the sides in half. So when I'm thinking about that multiplier, it's called a ratio. So the ratio of the corresponding sides are equal. In the triangles that I have here, again, triangle ABC is similar to triangle DEF. So I know that AB, the side going from AB, is going to match up with side DE. Another ratio of sides would be the side BC, and it would match up with the side EF. And finally, the third pair of sides would be A to C, and it matches with D to F. If I were to fill in the numbers that I've given in the question for each of these sides, I've got 6 sides there. I'm just going to go to the triangle. I know that side AB is 5 units long. Side DE is 10 units long. And then for the second ratio, side BC is 11 units long. Side EF, I don't know that length. So I can either call that side EF again, or because EF is across from angle D, I know that it's little d. So the side lengths have little letters, and the angles have capital letters. For the third pair of sides, side AC is 8 units long, and side DF, again, I don't have a letter there, so across from DF is angle E. I can see that it's pointing over here at DF, so I can call that side little e. Now what I'm noticing is that when I went from the small triangle to the big triangle, I multiplied by 2, so I'm doubling the side lengths. I can also think about it as cutting in half if I was going the other way. So if I wanted to find the side lengths of the other two sides, I could take the smaller triangle and multiply the side by 2 to find the corresponding side length in the other triangle. The third property of similar triangles is that the ratio of the areas is equal to the square of the ratios of the sides. So I would only ever use 2 of these given fractions or ratios. So I would always think about using my area ratio in this question. If I wanted to compare the two areas, and I'm going to use the triangle from the question above, I could choose any one of the pairs of sides. I could use a B and DE, BC and EF, or AC and DF. Because the question above gives me side AB and side DE, I'm going to use that first pair. So I knew that the ratio of the side lengths was that it was doubling. But the ratio of the areas is a little bit different. I know that side AB is 5 and side DE is 10. And I need to square those in order to find my relationship. When I square a fraction, I square the top number and I square the bottom number. So what I see here is that the ratio between the two areas is actually 1 to 4, or 25 to 100. The area of the bigger triangle is 4 times the size of the area of the small triangle. So a little bit different than the comparison of the side lengths. Moving on to the back of the page, we've got 2 examples to go through. So the first one, I'm given the information that triangle ABC is similar to, don't forget that's what that symbol means, triangle FGH. Now, when they give me the triangle names, they've already matched up the corners for me. So I know that corner A matches with corner F, and corner B matches with corner G, and finally corner C matches with corner H. In this picture, they haven't been spun around at all, so they match up quite nicely in the picture. What they want me to do is find side G. So I'm going to set up the ratios of all of the sides. Since I'm focusing on the sides, I'm using property 2 from the other side of the page. In this question, if I'm going to use side G, I also need to use its matching side, which is AC in the other triangle. Instead of using all 3 ratios or all 3 fractions, I'm only going to use 2. So I only need 1 more pair. Since I don't know anything about F to G, I'm going to use the G to H side and its matching side in the other triangle, which is B to C. So those are my 2 ratios. I can choose to put the bigger triangle on top or the smaller triangle on top. I'm going to put the smaller one on top, so AC goes on top of its matching side, FH. And again, smaller one on top, BC goes on top of its matching side, GH. And now I can fill in what I know. I know that side AC is 5, and FH is my little g. And then the other ratio is 4 to 12. Just like yesterday, we know that there are 3 ways that I can solve ratios, 3 standard ways that I went over. The easiest one is to look for a comparison between numbers, and I happen to see that here. I might not always see that, but going from 4 to 12, I see a multiplication relationship of times 3, and so I can use that same relationship in the same direction on the other side. So I know that G is equal to 5 times 3, or G is 15. And I'll just go back and take a look at my picture and ask myself, does it make sense that side G equals 15? And it does. It makes sense that the hypotenuse of that triangle is longer than the other side that was given. In example 2, again, we're given that triangle ABC is similar to triangle XYZ. So this is a little bit trickier because they have spun the triangle on me, but I know that angle A and angle X are going to match up together. Angle B and angle Y are going to match up together. And angle C and angle Z are going to match up together. I need to find the length of YZ. So what they're asking me to find is across from angle X, little x. The side that matches with YZ, going from my green dot to my blue dot, is BC. So I need to use that fraction, BC over YZ. Just out of habit, I'm going to keep the smaller triangle on top and the bigger one on the bottom, but it does not matter. The other side length that I'm going to use is going to be X to Z, because that's the only other side length that I have in the bigger triangle. Now that goes from the yellow dot to the blue dot, so I know that I'm using AC in the smaller triangle. Smaller triangle on top, bigger triangle on the bottom. And now I can fill in what I know. At this point, I could use two different methods to solve this ratio. I could use isolation by flipping both sides of the ratio and then multiplying to get rid of the 60. Or I could use cross multiplication, and that's what I'm going to show you here. So I'm going to do multiplying 60 times the bottom on the other side, 83. And then on the other side of the equal sign, I'm going to do the top to the bottom again, 61 times x. Now, I want to be able to get rid of that 61x. So first, I'm just going to simplify, get rid of the times sign, and I can just write 61x. And on the other side, this is equal to 10,980, if I do that multiplication. To get rid of the 61 times the x, I have to divide both sides by 61. And I end up that x is equal to 180, and there were units given to me in the question, centimeters. I'm going to scroll back up and ask myself, does that answer make sense? So I think that x is 180 centimeters. Now notice that the green line is a little bit bigger than the red line in the big triangle, and over in the other triangle, the green line again is a little bit bigger than the red line. So I'm pretty happy with that answer. It seems to make sense to me. My work for today is on the sideboard. Applied students are working on page 25, and academic students, you're on page 361. Good luck.